Okay, so vibrating string wave equation. We are going to derive the wave equation by taking the case of a vibrating string. This vibrating string, it can be the string of a piano, it can be the string of a guitar, it can be the string of a violin, and so on. So we are going to derive the wave equation by using the example of a vibrating string. Okay, so let us derive the equation modeling small transverse vibration of an elastic string, such as a violin string. We place the string along the x-axis, stretch it to a length capital L, and fasten it at the ends x equal to 0 and x equal to L. We then distort the string and at some instant, let us call it t equal to 0, and we release it and allow it to vibrate. The problem is to determine the vibrations of the string, that is to find its deflection, that is given by u is a function of x and t at any point x and at any time t greater than 0. Okay, uxt will be the solution of a partial differential equation that is the model of our physical system to be derived. So what if we here I think there has been some page jumbling though. So first page okay, what do we have here? We have a string stretched along the length of along the direction of the x-axis. At x equal to 0, one end of the string is fixed. At the other end, L equal at x equal to L, the other end of the string is fixed. Then we make the string vibrate, oscillate. We make the string oscillate about the x-axis, oscillate about the x-axis. Okay, so this is the picture, and we're going to make some physical assumptions before we proceed. Okay, and what are the physical assumptions? The physical assumptions are this. Number one, the mass of the string per unit length, the mass of the string per unit length is constant. That is, we are using a homogeneous string. The string is perfectly elastic and does not offer any resistance to bending. I repeat, the string is perfectly elastic and does not offer any resistance to bending. Okay, this is the first physical assumption that we have. And the second assumption is that the tension caused by stretching the string before fastening it at the ends is so large that the action of the gravitational force on the string can be neglected. I repeat, we are neglecting the action of the gravitational force on the string. There is the gravitational force which is trying to pull it down. We are going to neglect that because the tension in the string is much larger than the gravitational pull. Then third assumption, the string performs small transverse motion in a vertical plane. The string performs small transverse motions in a vertical plane. That is, every particle of the string moves strictly vertically. That is, every particle of the string moves strictly vertically, either vertically up or vertically down. It does not move horizontally. And so that the deflection and the slope at every point of the string always remain small in absolute value. So I repeat, the string performs small transverse motions in a vertical plane. That is, every particle of the string moves strictly vertically, and that the deflection and the slope at every point of the string is always remain small in absolute magnitude. Here I have drawn the deflection by exaggerating it. Sidadi ay deflection ji yam chawna kezi chigi alpha beta gi value ji ay denote nungaina bani, but ideally the deflection should be very small, very small deflections. Okay, I have drawn it an exaggerated picture so that alpha and beta can be easily identified. But in physical, but physically we assume that the vibrations are the deflections are very small. Under these assumptions, we may expect solutions that describe the physical reality sufficiently well. Okay, I repeat, under these assumptions, we may expect solutions that describe the physical reality sufficiently well. Okay. So the model of the vibrating string will consist of a partial differential equation and additional conditions. To obtain the partial differential equation, we consider that the forces acting on a small portion of the string. I repeat, to obtain the partial differential equation, we consider the forces acting on a small portion of the string. Here, PQ is a small portion of the string. Okay, and we are considering the forces that act at the point P and at the point Q. Okay, so this is a magnified picture of this portion. Okay, and since the string offers no resistance to bending, the tension is tangential to the curve. The tension is tangential to the curve of the string at each point. Okay, let T1 and T2 be the tensions at the endpoints P and Q of that portion. So at P, the tension is tangential to the curve and it is given by T1, and at Q, the tension is tangential to the curve at the point Q, and the tension at Q is given by T2. Okay, so T1 is the tension at the point P, T2 is the tension at the point Q. Here I have drawn it in a magnified way. T1 is the tension at the point Q, T1 is the tension at the point P, T2 is the tension at the point Q. And T1 makes an angle alpha with the horizontal line, and T2 makes an angle beta with the horizontal line. Okay, that is, horizontal line is the x-axis. I repeat, T1 makes an angle alpha with the x-axis, T2 makes an angle beta with the x-axis. Then, since the points of the string move vertically, there is no motion in the horizontal direction. Hence, the horizontal components of the two tensions, I repeat, hence the horizontal components of the tension must be constant. And using the notation shown in figure, using the notation shown in this figure, so what are the horizontal components now? The horizontal component of the tension at the point P will be T1 cos alpha, T2 cos beta. Okay, the horizontal component at the point P will be T1 cos alpha, and the horizontal component of the tension at the point Q will be T2 cos beta. So these two should be equal. That is, T1 cos alpha should be equal to T2 cos beta. And since it is a constant, we call it capital T. Okay, where capital T is a constant. Then in the vertical direction, we have two forces, namely the vertical components minus T1 sine theta, minus T1 sine alpha and T2 sine beta. Here, let us look again. T1 is directed downwards. So the vertical component of T1 will be minus T1 sine alpha, and T2 is directed upwards. So the vertical component of T2 will be T2 sine beta. Okay, so this is minus T1 sine alpha. This is minus T1, minus T2. I repeat, the vertical component of T1 will be minus T1 sine alpha, and the vertical component of T2 will be T2 sine beta. Okay. Here, minus T1 sine alpha and T2 sine beta of T1 and T2. Okay. Here, here the minus sign appears because the component at P is directed downwards. Okay. Now, by Newton's second law, the resultant of these two forces is equal to mass of the portion times the acceleration. And the mass of the portion is given by rho delta x. Okay. Here, rho is the mass per unit length of the wire. Okay. Or the mass per unit length of the string. And this acceleration, this is rate of change of displacement, second order rate of change of displacement with time. Okay. So second order derivative with respect to time of displacement is acceleration. And here u is a function of x and t, so we have taken partial derivative. Okay, and this partial derivative is evaluated at some point between x and x plus delta x. That is, this partial derivative is calculated at some point between these two, anywhere between these 2 points. Okay. Here, rho is the mass of the undeflected string per unit length, and delta x is the length of the portion PQ of the undeflected string. Hence, T2 sine beta, that is the vertical force upward at the point Q, minus T1 sine alpha, that is the vertical force downward at the point P. So T2 sine beta minus T1 sine alpha should be equal to mass times the acceleration. That is Newton's second law. Net force in the upward direction is equal to mass times acceleration. Then we already know that the horizontal components are equal. That is T2 cos beta is equal to T1 cos alpha is equal to T. So I divide both sides by equation number 1. So here I divide by T2 cos beta. Here I divide by T1 cos alpha. Okay. So T2 will cancel out sine beta by cos beta, that is tan beta. T1 will cancel out sine alpha by cos alpha, that is tan alpha. Okay. So we have rho delta x, here rho delta x divided by T, then the acceleration term. Okay, now this tan alpha and tan beta, these are the slopes of the string at the points x and x plus d delta x. So tan alpha and tan beta are the slopes of the string at the point P and Q respectively. So tan alpha is the slope calculated at the point x, tan beta is the slope calculated at the point x plus delta x. That is, tan alpha is the slope calculated at this point, tan beta is the slope calculated at this point, x plus delta x. Okay, so when I substitute tan alpha equal to this and tan beta equal to this in equation number 2, then equation number 2, this equation becomes slope at x plus delta x minus slope at x is equal to rho delta x by T, the acceleration. Now, if I divide both sides of equation number 3, if I divide both sides of equation number 3 by delta x, this delta x, then I have 1 by delta x is slope at x plus delta x minus slope at x. This is equal to rho by T times the acceleration. Now you take the limit. Now you take the limit delta x tends to 0. Okay. So in the limit, so if we let delta x tends to 0, then we obtain the linear partial differential equation. So if you take limit delta x tends to 0, then this becomes the second order partial derivative of u with respect to x. Okay, so we get the second order partial derivative of u with respect to x, and this term rho by t, if I bring it towards the left, it becomes t by rho, and t by rho we write as c square. This t by rho we write it as c square. So if we let delta x approach 0, we obtain the linear partial differential equation, this equation where c square is equal to t by rho. This is the one-dimensional wave equation. This is called the one-dimensional wave equation. We see that it is a homogeneous partial differential equation, and also it is of second order. Here we have second order derivative. Here we have second order derivative with respect to x, second order derivative with respect to time. The physical constant t by rho is denoted by c square to indicate that this constant is a positive constant, and ultimately this c will turn out to be the speed of the traveling wave. Okay, fine. Now we shall derive some additional conditions. So we have derived the differential equation. Now we shall derive some additional conditions. Since the string is fastened at the ends x equal to 0 and x equal to L, we have the two boundary conditions. That is, u at x equal to 0 for any time is equal to 0, and u at x equal to L is again equal to 0. That is, the string is fastened at the two ends x equal to 0 and x equal to L. These two conditions are called the boundary conditions. Furthermore, the form of the motion of the string will depend on its initial deflection. That is deflection at the time t equal to 0. So initial deflection, that is the deflection at the time t equal to 0, let us call it f of x. And its initial velocity, let us call it g of x. So initial deflection of the string, let us call it f of x. Initial velocity of the string, let us call it g of x. Then we have two more initial conditions. That is u at initial time, there is a displacement at initial time is equal to f of x, and the velocity at initial time that is equal to g of x. Okay, for all values of x from 0 to L. So these two conditions are called initial conditions, and these two conditions are called boundary conditions. So we have to solve the differential equation, which is the wave equation here, given here, one-dimensional wave equation subject to the boundary conditions given by equation number 5 and the initial conditions given by equation number 6. So this is how we derive the equation of wave in one dimension, and we also derive the boundary conditions and initial conditions. Okay, so let me stop the recording here.